Every day, 90,000 flights take off burning the same fuel as 1950: kerosene, carbon, noise. A century of aviation built on combustion. Now engineers are replacing that fire with something older than Earth: liquid hydrogen, 3 times the energy of jet fuel, zero carbon. In 2023, a pilot flew on it for 3 hours. This is how jet fuel dies and what replaces it. Hit subscribe because the future of flight just got a whole lot quieter. Aviation has run on the same basic fuel for over a century. Jet fuel, kerosene, was cheap, stable, energy-dense, and the whole world built around it. Airports, pipelines, refineries, an entire civilization of infrastructure locked to one molecule. By 2024, aviation was responsible for roughly 2.5% of global CO2 emissions. Small on paper, but aviation emissions grow 3 to 4% every single year. And unlike cars or factories, you cannot simply plug a plane into a battery. Batteries carry 60 times less energy per kilogram than hydrogen, far too heavy for flight. Sustainable aviation fuels exist, but they still burn carbon. The chemistry doesn't change. Hydrogen had been floated as an aviation fuel since the 1950s and dismissed. Too volatile, too bulky, too expensive to store at -253 degrees. In 1988, the Soviet Union actually flew a plane on liquid hydrogen, the Tupolev T-155, one engine modified, proof of concept, nothing more. The Cold War ended, oil stayed cheap, hydrogen aviation went back into the drawer. But two things changed in the 2010s: the climate emergency and material science. Lighter cryogenic tanks, better insulation, fuel cell technology borrowed from the automotive industry. For the first time, the numbers started to make sense, at least for short routes. Hydrogen doesn't just cut carbon. When used in a fuel cell, the only exhaust is water. No CO2, no soot, no nitrogen oxides, just water vapor leaving the engine. That single fact made engineers look again, seriously this time, with funding behind them. The European Union committed billions to clean aviation research through its Clean Aviation Partnership. By the mid-2020s, hydrogen aviation had moved from fringe theory to serious engineering program. There are two ways to fly on hydrogen, and they work very differently. The first is combustion. Burn hydrogen in a modified turbine instead of kerosene. Rolls-Royce has already tested hydrogen combustion in a ground-based jet engine. Hydrogen combustion produces no CO2, but it still produces nitrogen oxides at high temperatures. The second approach, fuel cells, is cleaner, quieter, and more efficient. Hydrogen and oxygen react electrochemically, producing electricity, heat, and nothing but water vapor. That electricity drives electric motors, turning the propellers. No combustion required at all. But storing hydrogen on board an aircraft is where the real engineering begins. Liquid hydrogen must be kept at -253 degrees Celsius. That is just 20 degrees above absolute zero, the coldest possible temperature. The tanks must be perfectly insulated, or the hydrogen boils off and is lost. This boil-off problem means ground time must be minimized. Hydrogen cannot just sit on the tarmac. New composite materials and aerogel insulation have dramatically reduced boil-off rates in recent years. The tanks are also 4 times larger by volume than an equivalent jet fuel tank. That means redesigning the aircraft. Tanks move into the fuselage, not the wings. Conventional wings store fuel in sealed cavities. That entire architecture has to be rethought. Weight is the enemy of flight, and cryogenic tanks add significant mass to any aircraft. Engineers are solving this with carbon fiber composite tanks, lighter, stronger, and cryogenically stable.
Getting the technology airborne required someone willing to actually build it and fly.
Stuttgart, Germany. A small aerospace company called H2Fly had spent years on one question. Could a passenger aircraft fly on liquid hydrogen, not compressed gas, but liquid? The difference matters enormously. Liquid hydrogen holds far more energy in far less space. Their aircraft was the HY-4, a twin-fuselage, four-seat hydrogen fuel cell plane. H2Fly's chief executive, Joseph Kahlo, had been building toward this moment for a decade. In September 2023, the HY-4 took off from an airfield near Maribor in Slovenia. It carried 10 kilograms of liquid hydrogen stored at minus 253 degrees. The flight lasted over 3 hours, a world record for hydrogen aviation. It was the first time a piloted aircraft had flown on liquid hydrogen anywhere on Earth. The HY-4 proved that liquid hydrogen could power real flight, not just a simulation. H2Fly reported that liquid hydrogen doubled the aircraft's potential range versus compressed gas, from 750 kilometers on compressed gas to 1,500 on liquid hydrogen. That range figure suddenly made short-haul regional routes, the busiest in Europe, viable. The Heaven Project, Hydrogen Aviation Experimental Network, had proved its central thesis. But a small experimental aircraft over Slovenia is a long way from a commercial airliner. The question now was whether the technology could scale and who would do it. Across the Atlantic, a British-American company called ZeroAvia was asking exactly that question. ZeroAvia's founder, Val Miftakov, had one goal: certify a hydrogen powertrain for commercial use. Their ZA 600 system targets 19-seat regional aircraft. The Dornier 228 was their testbed. In September 2025, ZeroAvia completed a full simulated flight profile, 2 hours and 38 minutes. The simulation covered a 250 nautical mile route without leaving the ground.
ZeroAvia's ground simulation wasn't just a test, it was a certification milestone. In March 2026, the FAA published special conditions for ZeroAvia's electric engine component. Special conditions are how regulators handle technology that existing rules were never written for. It means the FAA is actively working out how to certify hydrogen aviation right now. But ZeroAvia's path to full certification has not been smooth by any measure. In early 2026, the company cut approximately half its workforce due to funding constraints. Full ZA 600 powertrain certification has been pushed back by 12 to 24 months. The fuel cell system alone is now targeted for certification in 2027 at the earliest. Full powertrain certification, engine, tanks, and integration is realistically looking at 2028 to 2029. These delays are real, but they reflect the scale of the engineering challenge. No hydrogen powertrain has ever been certified for commercial passenger aviation anywhere in the world. ZeroAvia is not alone. KLM Royal Dutch Airlines has committed to a demonstration program. KLM has announced plans to demonstrate liquid hydrogen flight on an ATR-72-sized aircraft in 2026. That aircraft carries up to 70 passengers, a significant step up from 19. The performance data from H2Fly remains the most concrete proof point in the field: 3 hours and 10 minutes of powered flight, 10 kilograms of liquid hydrogen consumed, 0 carbon dioxide emitted during the entire flight, verified by DLR, Germany's aerospace agency. Liquid hydrogen extended the HY-4's range from 750 to 1,500 kilometers, verified. Fuel cells running on liquid hydrogen are 30 to 40% more efficient than turbines. These numbers tell a consistent story. The technology works. The timeline is just longer than hoped. The science is not the bottleneck. The infrastructure and the certification process are. Airports currently have no liquid hydrogen refueling infrastructure, not a single commercial terminal globally. Jet fuel pipelines run beneath virtually every major airport in the developed world. Replacing or supplementing that network with cryogenic hydrogen systems is a decades-long infrastructure project. Estimates suggest full hydrogen airport infrastructure could cost hundreds of billions of dollars globally. That cost means hydrogen aviation will arrive first on short regional routes, not transatlantic. Regional routes under 1,500 kilometers represent the most viable entry point for hydrogen aviation.
Airbus, the world's largest aircraft manufacturer, centralized hydrogen aviation as its core climate bet. Their ZEROe program originally targeted a hydrogen-powered commercial aircraft entering service by 2035. In February 2025, Airbus delayed that target by 5 to 10 years. The ZEROe budget was cut by 25% and the A380 fuel cell test was canceled. Airbus cited immaturity of hydrogen technology and uncertainty around airport infrastructure as the reasons. That decision sent a chill through the hydrogen aviation community, but it was honest. In March 2025, Airbus recommitted, but to a fuel cell concept, not hydrogen combustion. Commercial hydrogen aviation from Airbus is now realistically a 2040s proposition, not 2030s. But the Airbus delay reveals a deeper problem that goes beyond engineering, the hydrogen itself. Today, over 95% of the world's hydrogen is made from fossil fuels. Gray hydrogen, made from natural gas, produces significant CO2 during its own production process. Flying on gray hydrogen would simply move the carbon emissions from the sky to the ground. Green hydrogen, using renewable electricity, produces zero carbon across its entire life cycle. But green hydrogen currently costs 3 to 6 times more to produce than gray hydrogen. Scaling green hydrogen production to meet aviation demand is itself a decades-long energy transition. There's also a harder ethical question sitting underneath all of this engineering progress. Does the promise of future hydrogen aviation give airlines permission to delay action today? Climate scientists call this moral hazard, using future solutions as an excuse to avoid present ones. Sustainable aviation fuels exist today and can cut life cycle emissions by up to 80%. SAF adoption is running at under 1% of global jet fuel consumption right now. Hydrogen aviation and SAF are not competing. Aviation needs both, on parallel tracks, urgently. Safety is the other conversation that aviation regulators are having very carefully behind closed doors. Hydrogen has a wider flammability range than kerosene. It ignites at lower concentrations in air. But hydrogen also disperses faster than kerosene. It rises and dissipates rather than pooling. The safety profile is different, not necessarily more dangerous, but different in ways that demand new protocols. What the next decade actually looks like is becoming clearer if you read the signals carefully. Small regional hydrogen aircraft, 19 to 70 seats, enter commercial service around 2028 to 2030. Narrow-body hydrogen aircraft, the workhorses of short-haul aviation, are a 2035 to 2040 proposition at best. Long-haul hydrogen aviation, wide-body transatlantic routes, is unlikely before the 2050s, if ever. But here is what matters. The trajectory is real, the milestones are verified, and the direction is set. Every decade that passes without acting on aviation emissions makes the problem harder to solve. Liquid hydrogen aviation is not a fantasy. It is an engineering program with a schedule. Aviation is one of the hardest sectors to decarbonize. Hydrogen is the most credible path forward. Battery electric aircraft hit a physics ceiling. Energy density simply cannot scale for flight. Synthetic fuels require enormous amounts of renewable energy to produce at meaningful scale. Hydrogen sits in a unique position. High energy, zero carbon at point of use, scalable production pathway. The next 10 years will determine whether hydrogen aviation becomes the norm or stays niche. Jet fuel ruled the skies for a century, but its reign is finally ending. What replaces it will be quieter, cleaner, and built on a molecule older than Earth.
The sky going silent is not a dream. It is an engineering program already underway. The roar of the jet age just met its match. Hit like, share this with someone, and subscribe to SynthCosmos. We cover the science reshaping our world as we know it every single week. We'll see you in the next one.